Dear colleagues, dear professors and the students, welcome to today's Systems Analytics Global Leader Seminars. So today we are very happy to invite Professor Francisco Saldanha Gama to deliver seminars for us. So first, let us to introduce to talk about more on the seminar first. So the seminar is the goal of the seminar is to provide a platform to connect the global academics and researchers in many different areas in industrial engineering, management science, and also a lot of broad application domains like construction, finance, healthcare, logistics, transportations, and manufacturings to share their significant ideas, insights with the participants, and also nurture the younger generations of researchers who will lead our future. So for the previous talk, we have already invited 21 global leaders to deliver very meaningful seminars for us. Here is their talks and their names. And for the upcoming speakers, we invited Professor Andrew Mata, who is the editor-in-chief of Flexible Service and the Manufacturing Journal, to deliver a seminar at the 4th of May. And also Professor Chin-Hin Kai, who is the co-editor of Industrial Management and Data Systems, to deliver the seminar on June the 1st. So, okay. So today, we are very happy to invite Professor Francisco Saldanha Gama to deliver a seminar for us. So first, let me briefly introduce Professor Francisco. So Professor Francisco is a professor of operations research at the Department of Statistics and Operations Research at the Faculty of Science, University of Lisbon, Portugal. He received his PhD in the same place in 2002, and his research direction is in decision-making under uncertainty, discretized optimization, location theory, and project scheduling. And he has already published many papers in areas of location analysis, supply chain management, logistics, and combinatorial optimization. He also received a lot of awards, including the EJOR top cited articles from 2007 to 2011, and also the prize Roger Carbonian in 2020 by HEC Montreal, Quebec, Canada. And he is also a member of several international organizations, such as the EURO working group on location analysis, and he is one of the past coordinators. Currently, Professor Francisco is the editor-in-chief of Computers and Operations Research, and also he is a member of editorial advisory board of the Journal of the Operational Research Society, and also the Operations Research Perspectives. So today, the topic of his talk is capturing the uncertainty in districting problems towards more comprehensive modeling frameworks. So let's welcome Professor Francisco. So please share your screen.
Okay, thank you very much.
Thank you very much.
Okay, so I'm going to share my screen. I think you are now, you can now see, I think, my presentation, right?
Yeah.
Yes. Right, in full screen?
Yes,
perfect.
In full screen now. Yeah.
Perfect. So thank you very much for the nice introduction. In fact, I was very much pleased by this invitation, because there's a long time since I wanted somehow to establish some connection with Hong Kong, because everybody knows that in Hong Kong there's very good people, very good researchers, in particular in the areas in which I have been doing most of my work, which is discrete optimization, operations research, logistics, supply chain management, and optimization under uncertainty. So this invitation was really a pleasure to me to accept. I was debating a little bit the topic I should present today. And as I was telling in the beginning to my hosts, since I didn't know very well the audience, I decided to bring one topic in which I have been working already for several years, which is on districting problems, which is, in my opinion, a very much applied topic. So that there are many applications, and you'll see that in just a few minutes. And on the other hand, there are some nice technical challenges in this type of problems. So usually we don't work alone. We always collaborate in science. And this is the good thing about science. So I must say that the presentation that I'm making today is somehow a presentation that results from different works that I have done with different people. And possibly not all the names are here, but I think that I put here all the names that somehow are involved in any part of my presentation. And the outline of the presentation is the following. First, I will talk generically about districting problems, because I want to make sure that no one gets lost. So I'm going to talk about the very basics. Then I will talk about how to capture stochastic uncertainty in this type of problems. And I will develop some basic, let's say, modeling frameworks that afterwards I will extend so that we get more comprehensive models in the sense that capture some features of practical relevance. And then I will present some computational experiments so that we understand how applicable are the models that I'm going to discuss in the presentation. So when we talk about the districting problem, actually, we talk about a problem in which we have a geographical area that consists of a set of territorial units, and we want to group these territorial units into a given number of larger geographical clusters, let's say, and this is what we call districts. I have here directly an example. So in this case, we have, let me see if I can put, the spotlight. I think, okay, I think we have it. Okay, do you see the mouse moving in my slides?
Yes.
Yes.
Okay, perfect. Thank you very much. So we have here a geographical area, and in this right-hand side figure, we see the division of this territorial area, this geographical area, into a certain number of districts, in this case, 5 districts. Well, the issue is that usually when we solve a districting problem, we use some planning criteria. And these planning criteria have to do with different things, namely 4 main aspects: integrity, balancing, compactness, and contiguity. Well, by integrity, we mean that each territorial unit is assigned to exactly one district. This is what we see in this figure. Every territorial unit has just one color, let's say. So it's assigned to exactly one district. By balancing, it means that usually there is some activity measure generated at every territorial unit. For instance, some demand for a service. And by balancing, we mean that we want districts whose global activity is more or less the same for all of them. Then we talk about compactness. This is a concept that is not very easy to define, but using a simple language, let's say that we want to build the districts in such a way that the territorial units in each district are fairly close to each other. And finally, we talk about contiguity. And contiguity means that when I want to go from a territorial unit in one district to another territorial unit in the same district, I don't need to cross a different district. So we don't have enclaves or exclaves. These are the basic principles. So I would say that the districting problem is actually like a clustering problem, but with a strong geographical component, let's say. There are many applications for this type of problems. This problem started to be studied in the US about political districting, but then other researchers have worked on that. There are applications in strategic service planning and management. For instance, in healthcare, there are several papers on that. School systems, again, several researchers have dealt with districting problems in the context of school systems. Energy and power distribution networks, design of police districts, this is a very nice application. Waste collection, this is another application in which districting is very relevant. In transportation in general, there are some interesting works done on that. In the design of commercial areas to assign sales forces, again, we see some works done on that. In distribution logistics, possibly a very natural application of districting problems. And well, these are the areas that I could think of, but possibly there are other type of applications. Well, as I told you, these areas started to be studied some time ago in the context of political districting. And in fact, people working in districting, usually they start their work from, in terms of mathematical modeling, from a well-known optimization model that I would like to revisit here, because I'm going to somehow use this model, or this model will be somehow at the core of everything that I'm going to present today. So this model was presented in a seminal paper, let's say, published in 1965. And the idea is, in fact, to create P districts according to 3 criteria: integrity, balancing, and compactness. So for the moment, we forget contiguity. We will talk about that later. One important thing is that the number of districts is, in this type of problems, given beforehand. So we know beforehand the number of districts we want to design, let's say. Well, we can. I'm going directly to present some notation. We will need that for other developments I'm going to present to you. I'm going to denote the set of basic territorial units by this capital I. I'm going to denote by DI the activity level generated at territorial unit I. Well, usually we have a kind of a term we use in districting for activity level, which is demand. But when we talk about demand, it is not necessarily the amount of some product that some territorial unit will buy or will sell or whatever, okay? So, but usually we call just demand to this activity level. So I'm going to keep using exactly the same term. Then, as I told you, there is an important geographical content in these type of problems. So we always consider the distance between territory units. And usually this is actually a road distance, or the distance we have to go with the transportation means that we have for underlying the problem. So this is a basic notation that I'm going to use later on. So how do we ensure balancing? I told to you that balancing is a very important feature in districting problems, to keep somehow balancing in terms of the activity level in the different districts. So every district generates a certain activity level, and we want to design the districts in such a way that more or less the activity levels in different districts are the same. How can we ensure this? Well, the classical way proposed in the seminal paper that I mentioned to you is to compute the average demand per district. How do we do that? Well, we just compute the total demand and we divide it by the number of districts. And then, of course, we know that we cannot get perfectly balanced districts Because, well, the demands are different. So it's usually not possible to have perfectly balanced districts. So what we do is to consider a deviation that I'm going to denote by alpha, which is the maximum deviation we allow with respect to this reference value mu. So what we impose is that the demand in the district should not deviate from the reference value more than a certain percentage. This is the way of ensuring balancing, and this is still used in many models that we see in the literature nowadays. Another feature of relevance in districting is compactness, and this is tricky. How do we capture and measure compactness? I have here two examples of two districts. These dots are actually territorial units, or if you prefer, the centroids of the territorial units. And if you look at the left-hand side figure and the right-hand side figure, you would say that the left-hand side figure is more or corresponds to a more compact district than the other one. And it's this visual perception that leads us to consider usually the distance between a territory unit I and the central territory unit, say O, of the district. And then what we usually do is to consider a cost that, for instance, can be equal to the distance or to the square of the distance, and that somehow tells us how costly is to include territory unit I in the district that has O as the central territory unit. And this allows us to compute a measure which is the sum of these costs for every district that somehow measures the compactness for the district. And this is still today what many people do. Well, this slide here tells us, and the previous one also tells us, that in the end, it's going to be important for every district to have somehow or a territory unit representing that district. And in fact, this is something quite common in modeling, when modeling districting problems, is that to assume that every district will have a territorial unit that will represent it, the, say, center of the district. And then when we say that territorial unit I is assigned to territorial unit J, what we are actually saying is that territorial unit I is in the district represented by territorial unit J. And using this type of terminology, it's fairly easy to come up with a mathematical model for this basic problem. We just need to consider binary variables, let's call them xij, that for every I and every j are equal to 1 if territory unit I is assigned to territory unit j and 0 otherwise. So if for some j we have xjj equal to 1, this means, using this variable definition, that territory unit j is assigned to itself. And this is an elegant way of saying that we have just selected territorial unit j as the representative, or the center, if we prefer, of its district. Well, using these binary variables, we can come up with this mathematical model in which we want to minimize this compactness measure. And then we want to ensure that every territory unit is assigned to exactly one district. We have exactly P districts. These constraints here are the balancing constraints. So they say that the activity level generated at the district represented by J should be within the limits imposed. So we have here the reference value and here the maximum deviation. Okay, it's for both sides. These constraints here state that I can only assign a territorial unit I to a territorial unit J if in fact territorial unit J has been selected as the representative of a district, and then we have the domain constraints for our decision variables. So when we look at this model, we see a little bit of everything that I mentioned to you. We see compactness, we see integrity, we see p-districts, we see balancing, well, in the integrity again, and the location, of course. You may ask, and what about contiguity? This is a good question. Actually, in the beginning, this was the model that was proposed, and still much research relies on this model, because what researchers observed is that in many cases, compactness favors contiguity. So in many cases, compactness, or a good compactness measure, is a good surrogate measure for contiguity. And this avoids making the models too heavy. And because the models become a little bit lighter, we can do more things with them and eventually embed other features of relevance. And this is exactly what I'm going to do today. In fact, there are some papers discussing specifically the inclusion of contiguity constraints. We can do that. So constraints that impose explicitly that we have contiguous solutions. So we never have to cross a different district when we travel between territorial units in the same district. But in this presentation, I'm going to use actually this compactness measure as the surrogate measure for contiguity. If you want, I can give you some hints about the inclusion of contiguity constraints later on, because there are some nice papers on that. Well, when we look at this model, and I don't know if you are well acquainted with the facility location problems. In fact, when we look at the model that I'm projecting now, we see a discrete p-median problem with extra constraints that are the balancing constraints. This is interesting because this is exactly what relates districting problems with facility location problems and location science. So it's not unusual to see people from location science, and this is my case, working on districting. Another interesting aspect about this model is that, in fact, these constraints here are not necessary. Because you see, the balancing constraints ensure this. If xjj is equal to 0, then I cannot assign any territorial unit to territorial unit j. However, I'm going to keep these constraints here because they will be helpful in some developments I'm going to present later on. So, well, more than helpful, they will be actually needed. That's why I decided to include them directly here. Moreover, if we ignore the balancing constraints, we have directly a p-median problem, a discrete p-median problem. And this is something that I like very much to see and to build these bridges between different topics. Well, but a major aspect in my talk today has to do with uncertainty. And the only source of uncertainty that we see in this type of problems has to do with the activity levels in the different territorial units, because these costs are built from the distances, and the distances are what they are. So I would say that the only source of uncertainty that we can find here has to do with the demand of the territorial units. So one important aspect is how do we cope with changing demand in districting problems. And before going into the core of my talk, I'd like to show you different perspectives. In fact, in practice, demand may change. There are many reasons for that. It may be the expansion of urban areas, so we have new territorial units added to the geographical area of interest, or migration flows, economic conditions, and possibly many other reasons. So it's not difficult to find in practice situations in which we have a demand that changes over time. And the question is how to hedge against such changes. Well, the answer is quite straightforward. It depends on the specific problem we are trying to solve. And there are different possibilities for hedging against demand changes in districting problems. I could think of three possibilities. Possibly there are more, but one is redistricting, what we call redistricting. Another is multi-period districting, and the third one is districting under uncertainty. I put here some dots because possibly there may be some others that I overlooked. But I would say that these three are possibly the most important ones to deal with changing demand in districting. When we talk about redistricting, we are talking about a problem in which the demand changing has already occurred. And we adopt a reactive posture. So we are reacting to what has happened. And what we do is to solve what we call a redistricting problem. And the idea is just to solve, well, a new districting problem using the new conditions. This is the idea underlying a redistricting problem. So a redistricting problem is nothing else than a districting problem solved after another districting problem. And then we have multi-period districting. This is interesting. Actually, I'm also doing some work in terms of multi-period districting, although I'm not talking about it today. And the idea here is that demand has still not changed. So we know that we are dealing with a demand that can change, but the change has still not occurred. Moreover, this is a setting in which the demand changes can be predicted for some future that we call the planning horizon. And in this case, we can adopt a proactive posture, which means that we look for solving what we call a multi-period districting problem. And the main goal is to devise a plan. And the plan means a way of building the districts and adjusting them over time so that we cope with the varying demand in the best possible way. This is a second possibility for working with changing demand in the context of districting. And the third one is to capture somehow uncertainty in the demands in our districting problem. So we have uncertain demand, we don't know it. And what is more, we cannot forecast it accurately. Still, we want to adopt a proactive posture. Well, and what we have to do is to capture somehow the uncertainty in our problem. And so we have to develop models that somehow capture uncertainty in the demand. There are different paradigms that we can use here. We can go in the direction of what we call online optimization. This is a strategy usually followed when we are dealing with short-term uncertainty. Then we can go in the direction of robust optimization. This is certainly a direction in which I would like to go in a very near future, and I think I'm starting that in the very near future. And the idea is to represent uncertainty using what we call uncertainty sets. So demand is represented by what we call uncertainty sets. And finally, we have stochastic programming. In this case, uncertainty is described by some probability distribution. And this is actually the case I'm going to consider and to discuss with you in this talk. So let's start from the very beginning. And the very beginning in stochastic programming is usually a two-stage stochastic programming model. Let's discuss a little bit the ingredients for building a mathematical model capturing stochasticity in the demand. So overall, we have a problem in which we seek to plan for the organization of a geographical area into districts. This is a districting problem. The issue is that we must make a here and now decision about the districts, but we still don't know the demand. What do we know about the demand? We know that the demand is stochastic, so we can represent it by some random vector. And let's assume that we know the cumulative distribution function of this random vector. we can estimate it, for instance, using historical data. So let's assume in this talk that we know the cumulative distribution function of our random vector. How can we make a decision? Well, we have to make a decision now, but we don't know the demand. So we need to make a here and now decision. And the here and now decision is just a territory design. I must divide my geographical area into districts before knowing the demand. And so the question is this feasible when the demand comes? What is the problem about feasibility? Of course, it has to do with the balancing requirements. Because I can ensure that this solution is contiguous, is compact somehow, is integral in the sense that we don't split territorial units among different districts, and what about the balancing? The balancing, to know if this solution is balanced, we need to know the demand, but we don't know the demand. So under uncertain demand, what can we do? Well, we can try to look for a solution, a here and now solution that is feasible, no matter the demand that I'm going to observe. But this is quite difficult. And I'd say that it is very easy to build examples in which there is no initial solution that is feasible, whatever the demand that we are going to observe later on. So it's very easy to get non-balanced solutions. Even if it is possible, usually such a solution would be what we call too fat, in the sense that probably it would overlook too much other important criteria like compactness. So what can we do in this case? How can we make a here and now decision to hedge against some demand that we don't know beforehand? Well, a possibility is the following. Let's keep going. Let's make a here and now decision, and then let's wait for the demand. And when the demand becomes known, we can adopt what we call a recourse action. So we consider the possibility of having some decision that we can make after demand is disclosed that somehow complements the initial decision made and corrects it in case it is not feasible. I'm going to show you one possibility. So after we observe demand, we may conclude that the initial solution is infeasible. What does this mean? This means that in some district, in at least one district, the observed demand in that district is outside this balancing region that we defined in the beginning. So we may have, say, shortage with respect to these limits, or we may have surplus in terms of demand. So we have what we call an unbalanced solution. What can we do? One possibility is just to take some extraordinary actions to overcome shortage or surplus, depending on what we are observing. For instance, one possibility for handling shortage at some districts, shortage means that we have less demand than we expected, let's say. So one possibility is to downsize the workforce allocated to that district, and this may have costs, of course. And what to do if we have surplus in some districts? So we have more demand than our capability. Well, one possibility very much used in logistics problems is to resort to some outsourcing or to third-party company to help us handling the surplus that we have. Well, we can incorporate these extraordinary actions easily in our models. The only thing we need is to consider some extra variables that will represent the surplus or the shortage in every district. Of course, we are not going to observe simultaneously a surplus and shortage in a district. And then we can assume that we have some unit cost for surplus in a district and a unit cost for shortage in a district. If we consider these extra variables and these extra costs, then we can reformulate our original model. And the model can be formulated like this. So in black, in this slide, in black, you see the components of the model that define the initial districting solution. So we want to define variables for the xij variables so that we have a districting solution. The thing is that we don't know the demand that we are going to observe. So for every first stage or initial districting solution, we may have to pay some cost, some consequence cost for that districting decision that I'm representing by this function here, this calligraphical Q of X. Well, one easy way to cope with this future consequence that we don't know beforehand what exactly it will be is to consider that this consequence is actually the expected cost we are going to have in terms of the extraordinary actions if initially we adopt the solution that this black part of the model induces. Well, this problem here, Q of X psi, it's actually what we call, or the objective function of an optimization problem itself. And this is a problem that looks for the best way to handle shortages and surplus at the districts, somehow to correct the way the demand is handled in the districts so that we get balanced solutions. And of course, in this problem, we want to minimize the cost associated with these extraordinary actions. So this is what we call the second stage problem. This is a problem defined for every first stage decision. So in this problem, the X variables are known, and for every realization of the uncertainty. So if we have many realizations for the uncertainty, we have many problems like this to solve. But if the support of our underlying random vector is finite, then we can go a little bit further in terms of modeling. What we can do is to use a scenario, what we call a scenario indexed model. Well, we call a scenario to a realization of our random vector. And in fact, if the support of our random vector is finite, we can index the different scenarios in a finite set, say this capital S, and now we can just index in S the demand and the second stage decision variables. So we are going to have a demand originated at each territorial unit I under each scenario, and we have surplus at each district depending on the scenario, shortages depending on the scenario, and then we are going to assume that we know the probability associated with each scenario because, as we assumed in the beginning, we know the cumulative distribution function of the underlying random vector. So we assume that we know the probabilities associated with the scenarios. I'm not discussing in this talk too much how in practice we obtain these values. But one important thing to define now in this stochastic problem is our reference value to be used in the balancing constraints. Why? Because recall that the reference value was the average demand in the deterministic problem. But now we don't know the demand because demand is stochastic. So what is the reference value we should consider? There are different possibilities for handling these. And one that is, I would say, the most straightforward is to check the demand in each scenario, the total demand in each scenario, and then to compute the expected demand and to divide this expected demand by the number of districts. If we do this, we can finally formulate what we call the extensive form of our stochastic programming problem, in which we put all the scenarios explicitly in our model. So it's like we build a single model in which we have the first stage decision. This is represented by the X variables. And then we have here the expected cost associated with the extraordinary actions due to shortages or surplus at the different districts. And then we have a balancing constraint for every scenario. And this solves the issue in terms of modeling, of course. Well, but here we are being a little bit reactive to the existence of shortages and surplus. And in my opinion, and also in the opinion of some co-authors of mine who have worked together with these, we can enrich the set of second stage decisions. We can be a little bit more proactive than just handling shortages and surplus in a very simplistic way. What we can do is move some territory units across districts as another extraordinary action that we can make. Of course, this should be made up to some extent. And we talk about that later on. So the idea would be still to make a here and now decision and to say I'm directly organizing my geographical area into districts. And then when demand becomes known, I consider two types of recourse actions. One is to deal with shortages and surplus as before. And another one is to do what we have called redistricting, which means to move some territorial units from one district to another. For instance, in this case, there are 3 territorial units in green that we are moving to the blue district, and also some territorial units in the blue district in the beginning that we are going to move to this light green district in the second stage. So you see, the idea is we can keep dealing with shortages and surplus as before, but we can also change a little bit our territory design. Of course, we are not going to want to change too much because this would be solving the problem from scratch, and this is something that we want to avoid. But for that, we can also impose some constraints, as I'm going to show you. So let's keep assuming that uncertainty is captured by a finite set of scenarios. Okay, you can ask me in the end what we can do if this is not the case, but I can tell you directly the answer is that we have to resort to this case. So I'm not being too restrictive by considering this setting. So we need some additional notation now, especially because we want to account for the redistricting decisions. So we can denote by RIJS a cost that we are going to pay for reassigning territory unit I to territory unit J. This may have to do with costs for redesigning the districts, for instance, moving one workforce from one district into another, for instance. And then we need decision variables, again binary, that define the territory design in the second stage after demand is disclosed. So we may have a different territory design depending on the scenario. So we need binary variables indexed in the scenarios that will tell us whether we observe territorial unit I assigned to district J under a certain scenario. And to account for the reassignment costs, we need to check whether a territorial unit has moved from one district to another. And this is going to be represented by these V variables. VIJS will be equal to 1 if in the second stage territorial unit I is assigned to J, but this was not the case in the initial solution. So there was a reassignment of territorial unit I. Well, using this additional terminology, we can build up from the previous model, and I'm going to keep in black what we had already in the initial model, and I'm writing in blue the things we need to add to the model by considering the possibility of redistricting in the second stage. So we will have some redistricting costs. They will be scenario dependent. Now we no longer use here the binary I'm sorry, because I think you are not seeing, now you see the spotlight. Now here you no longer have the X variables. Why? Because the territory design may change from one scenario to another. And then we have a set of constraints that help us to ensure the consistency between the new variables and the existing ones. So here we say that no matter the scenario, all the territorial units must be in some district. These constraints here, I didn't talk about them before. Actually, there are special territorial units that we are not allowing to be moved from one district to another. And these are the representatives of the districts. And these constraints here prevent the representative of a district in the initial solution to be moved to another district. And why? Because if we do this, we totally distort, or we may totally distort the territory design by changing a representative. Okay, and we want to make some redistricting action without distorting too much our solution. And these constraints here using the V's just ensure the proper definition of the V variables. So they capture the fact that they represent a reassignment of a territorial unit. Well, this is, I would say, a possible two-stage stochastic programming model for handling uncertain demand in districting. But as I have already mentioned, there are some issues of practical relevance that we may need to capture in this model. One has to do with a maximum dispersion that we allow in a solution. Another has to do with the limitation in the number of reassignments in the second stage. To say, okay, I can reassign territorial units from one district to another, but up to some extent. Of course, if we put this limit, if we set this limit, it may be that we change all the territorial units in some district to another one. So in addition to this, we can also consider what we call similarity with respect to the initial districting. I will talk briefly about these three possibilities, and we can include all of them in the model. Well, when we talk about dispersion or territory dispersion, we mean the maximum distance between a territory unit and the center of the district it is assigned to. So suppose that we have a maximum desirable dispersion, let's call it Lmax, for the districting solutions we are seeking to obtain. Well, for the first stage solution, it's easy to impose this maximum dispersion. We can just say that I cannot allocate a territorial unit I to a territorial unit J if the distance between I and J is greater than the maximum dispersion that I have imposed. But then we can extend this reasoning to our stochastic problem and to the second stage solution. And so for every pair of territorial units I and J, such that the distance between I and J is greater than the maximum dispersion I want, and for every scenario, we must set these constraints. We must impose that these variables are equal to 0. This means that in no way I can assign I to J or reassign I in the second stage, putting it in the district represented by J. Of course, for every instance of the problem, there is a maximum absolute dispersion that makes sense to impose, which is the one resulting from solving the stochastic model. Okay, if we impose less than that or more than that, it makes no sense. I mean, it's not binding. We can of course impose, but it is not binding. Okay, so the maximum dispersion that makes sense to impose to make these additional constraints meaningful, in case they are, is if we have a maximum dispersion that is below the maximum dispersion induced by the optimal solution that we get by solving the stochastic programming model that I presented before. In terms of number of reassignments, in fact, as I told you, compactness in districting is very often used as a surrogate measure for contiguity. And the issue is that under uncertain demand, by adapting the solution according to the scenarios that we are going to observe, may disfavor compactness. So we can get a less compact solution, and this may endanger contiguity. So a natural extension to the problem is to impose a limit on the number of reassignments in the second stage. Well, this is very straightforward to include in our model. If M is the maximum number of allowed reassignments, we just need to say that the maximum number of V variables that can be equal to 1 is M, and this solves the issue. Finally, I'd like to talk about something that is a little bit more involved, which is when we impose a similarity with respect to the initial territory design. And the idea is that in some applications, it makes no sense to change too much the districts with respect to the original solution. And we can easily embed this situation in our model by using a set of constraints and imposing some similarity between the second stage districting plan and the first stage districting plan. How do we do this? We can do this using these new constraints here. What we have here, this is for every district and for every scenario. This is the number of territory units that were assigned to district J in the first stage. And this product is equal to 1 if a territory unit I was assigned to district J in the initial solution and keeps being assigned to the same district in the second stage solution. So there was no reassignment. So this is the number of territory units that were assigned to territory J, to district J in the beginning, and that keep assigned to it in the second stage. And what we are saying is that this is at least a certain proportion of the initial number of assignments. This is a way of imposing a similarity with the initial districting solution. So this gamma parameter is going to be a minimum proportion of territory units to keep together in the same district according to the first stage plan. Well, we have now a set of constraints that have a nonlinear term, but it's not difficult to linearize it. We just need to add some constraints. These constraints here say that if I reassign territory unit J, I to district J, then I have territory unit I assigned to territory unit J in scenario S. And these constraints here say that if initially territorial unit I was assigned to district J, then it cannot correspond to reassignment in the second stage. So this variable V should be equal to 0 and the other way around. So at most one of these variables can be equal to 1. And by imposing these constraints, we can reformulate these constraints here. And now this term here, I mean, this is equal to 1 when in scenario S, we have territorial unit I assigned to J, but this does not correspond to the reassignment. So this is equal to 1 when W is equal to 1 and V is equal to 0. So this means that the territory unit I is assigned to district J in the second stage, but it was already assigned to that district in the first stage. And this is a way to capture this similarity with respect to the initial plan. Well, I'm going to end my talk to present you some results. I don't want to bother you too much with figures and tables and that, so I will try to make this a little bit light. I have some results based upon the province of Novara. This is a province in the northern Italy. It has 88 municipalities. So we use the real geographical data and the real distances between these territorial units. As for the demand, in this case, we generated it randomly because we were not working with a specific application in the province of Navarre. So the geographical data is real, but the other data we generated to see how our models behave. So we consider a base demand generated in a simple way, and then we consider 3 scenarios for the demand. One in which we had demand 20% below the base values. Scenario 2 is actually, it corresponds to the base demand, and scenario 3 corresponds to 20% above the base demand. Then we consider 4 different types of probability distributions. We have a probability distribution which is a uniform across the 3 scenarios, and then we consider 3 non-uniform distributions. One of them is symmetric, which is distribution 3, and the other 2 are non-symmetric, because we wanted to understand a little how the solutions change with the type of distribution that we consider. As for the assignment costs, what we did was to make them dependent also on reflecting a little the probability distributions. So what we do is the following. The cost for assigning territorial unit I to district J is the distance between I and J weighted by the expected demand of territorial unit I. As for the reassignment costs, what we did was to consider them dependent on the distance between territorial unit I and district J in territorial unit J, the demand of territorial unit I under scenario J, because recall that the reassignment costs are scenario dependent, and then we consider a factor that allows us to play a little bit with these costs so that we understand what happens when they are higher or lower. Well, I'd like to show you some solutions. This is a nice thing about districting, is that we have a lot of colorful solutions to show. And in the particular case of this slide, we have actually the stochastic solution for a specific instance. This is one we want to build for districts. This is the 3rd probability distribution, which is the distribution that is not uniform, but it is a symmetrical one. This factor for the relocation costs, we set it equal to 1, which means that the relocation costs are just the distances multiplied by the demands. And alpha, I recall, is the tolerance, the maximum tolerance we accept with the reference value to say that the district is balanced. And for this instance, the solution, the optimal solution, the optimal first stage solution that we obtained is this one. In yellow, you can see, you see the representatives of the districts. And then we have the 4 districts in different colors. Well, what is the optimal second stage solution? The issue is that we have 3 scenarios for the demand. So depending on the scenario that you observe, we must adopt a different solution. We must consider 1 second stage solution for each scenario, and here they are. So for that first stage solution, depending on how demand is revealed, I see different territory designs adopted to hedge against the demand that we observe. As you can see here, this is the base model. So we are not imposing constraints on the maximum number of territory units that we can move, or we are not imposing some degree of similarity with the initial plan, okay? But what I like about this is that we see, even without imposing extra constraints, we see that we have the same type of solutions graphically with some adjustments. And this is what I like about stochastic programming, is that we see the solutions adapting, but not distorting too much the original one, but adapting to the occurring demand. The optimal solution to this instance is this value here, 3,463.2 for the data that we considered. But more relevant than this, and the specific value, is the following. Could we have done something different? Yes, we could. Suppose that we didn't want to capture uncertainty in our models, or we didn't want to work with the stochastic programming model. What could we do? Well, we could just compute the expected demand, because we know for every territorial unit, we have 3 values for the demand and we have probabilities. So we can compute the expected demand in every territorial unit. And then we can just solve the single scenario problem we would obtain for that expected value scenario, let's say. Well, I did this, and by doing so, we get another territory design. We get a solution which is eventually different from the one that we obtain when we solve the stochastic problem. And here it is. In fact, there are differences between this solution and the previous first stage solution that I showed you, and I'm going to put them side by side in 1 or 2 slides so that you check it by yourselves. But the issue is, suppose that we adopt this first stage solution instead of the first stage solution coming from the stochastic model, this one. Well, for this one, we have 3 second stage solutions. If we consider a different first stage solution, we will possibly get different second stage solutions, because of course the second stage solutions always react to the first stage solution. And if we adopt, say, the expected value solution, then we would obtain for the different scenarios these 2 solutions for scenario 1 and 3, and for scenario 2, it's not difficult to see that it's exactly the same as the first stage, because this is the average, because we are working with a probability distribution that is symmetric. The interesting thing here is that if we adopt this solution here resulting from the expected value problem, then the objective function, so we go to the stochastic problem and we set this first stage solution, and if we solve it, we get this objective function value. And I recall the optimal value of the stochastic problem. And in fact, we see that they are different. In fact, we see that there is a difference between what we can call a deterministic perspective, in which we replace all the random variables by their expected values. This is what we did. Or solving the stochastic problem, in which we explicitly consider all the values, the possible values for our random variables. And we see a difference here in the cost. This difference is what we call the value of the stochastic solution. And in fact, I computed the value of the stochastic solution for all the instances that we tested. And this is a figure showing it. We have the blue bars for the reassignment costs factor equal to 1, and the orange bars for a reassignment cost factor equal to 2, which means that in the case of the orange bars, say the relocation costs are the double of the ones corresponding to the blue bars. And this is the first thing we observe, is that in general, the value of the stochastic solution is smaller when the relocation cost is smaller. And why? Well, recall that the relocation costs more when this omega factor is higher. And interestingly, the expected value solution is not sensitive to this factor, since in a single scenario problem, we actually don't make any relocation. So it's not surprising that when the relocation costs are higher, then it makes more difference to solve the stochastic model instead of solving an approximation resulting from replacing all the random variables by their expectations. Then we see that the value of the stochastic solution seems to decrease. I want to, okay, here we have it. It seems to decrease when we increase the number of districts. So it seems that the smaller the number of districts we want to build, the more relevant is to solve the stochastic programming model instead of a deterministic approximation. Then there is another interesting thing, is that, and this is curious actually, I was not expecting this, is that apparently the first probability distribution seems to dominate the others. So it seems to be more relevant to solve the stochastic programming model instead of a deterministic approximation when we use a uniform distribution. And this is something interesting. Another interesting insight from this figure is that the intermediate values of alpha seem to give more emphasis to the need of solving the stochastic programming model instead of an approximation. And why is this? Well, first, because for small values of alpha, so we have smaller tolerance for considering a district as being balanced. In this case, of course, as soon as we make a reallocation, it's very easy to get a non-balanced solution. So this is the case in which the penalty costs for shortages and surplus become more dominant because we do less reallocations. And for larger values of alpha, of course, if we are more flexible, there's not so much to adjust. And this explains why the deterministic approximation can be a good one. Well, we designed, since I leave these notations here. Most of what I said, I think it's written there, so I can skip this slide. This is a figure showing that we computed something similar to the value of the stochastic solution, but ignoring the penalty costs for shortages and surplus. And why? Because in fact, what we have observed is that the penalty costs may blur the results. What we observe is that the value of the stochastic solution is smaller in terms of compactness. I mean, when we remove the penalty terms for shortages and surplus, but we observe still that the expected value solution provides a poor approximation to the stochastic problem. So what I have been discussing in these slides is it relevant to solve the stochastic programming model instead of a deterministic approximation? The conclusion is yes. Now, the second question, and possibly the most important one, is it relevant to capture uncertainty in our problem? Yes or no? The answer to this question is given by a value that stochastic programming inherited from decision theory, which is the expected value of the perfect information. And what we observe in this slide is that in general, especially for intermediate and small and small values of alpha, I mean, the less flexible we are in terms of considering a district balanced, the more important is to capture uncertainty. This is the main message from this slide. I prepare some more detailed conclusions, but I don't want to bother you too much about this, okay? As I told you, I'm not going to overload you in the presentation with results. I'm going to share the presentation with you if you want, and then you can check a little bit some details later on in case you are interested. Well, so far we focused the results on a single set of geographical data, which includes the 88 municipalities in the province of Novara in northern Italy. But to check the performance of the models, we extended that instance set by generating instances with 120, 60 and 40 territorial units. And then we just used an off-the-shelf solver to solve the stochastic programming model. And this is what we obtained in terms of performance of the solver. And what we observed basically is that even for the larger instances, most of them could be solved within a much reasonable time. So this is good. Why? Because it shows that we can solve up to proven optimality fairly large instances of the problem, of the base model. And this is good for two reasons. First, because most of the times practitioners are not well acquainted with specialized tools for discrete optimization. So the possibility of using a general solver is very important in practice, for people working in practice. The second reason why this is good news is that since we are able to solve fairly easily the base model, it makes sense to extend it. Okay, well, I'm running out of time, so I'm going to skip the results that I brought here about the extensions that I discussed, because well, this is interesting, I mean, but not so relevant, I would say, as the information that I was sharing with you. So I would go directly to an overview of this seminar. So I started by presenting some basic concepts on districting problems. I discussed different ways for hedging against changing demand in districting. I presented to you a two-stage program, a stochastic programming modeling framework for capturing stochastic demand. Then I enriched the model by capturing some additional features of practical relevance. And finally, I presented the results of of a series of computational tests performed using these models and based upon real geographical data. Well, districting is a very challenging area, I must say. I must share with you that I started working in districting almost by chance. Originally, I'm from location analysis, from discrete optimization, from optimization under uncertainty. And I had some colleagues in Italy, exactly, that were working in districting. And they wanted to capture uncertainty in districting problems because they were working with districting in a daily basis and in real applications. That's why when they invited me to join, because I knew a little bit, I had already some experience in terms of facility location under uncertainty. And as you could see from my talk, districting is very much about location analysis. And this is how it started. But there are many more things, in my opinion, that can be done. I think there are several research avenues. For instance, there's still very little work in terms of multi-period variants of the problem. To the best of my knowledge, there's 1 or 2 papers only in the literature. One thing that is also missing is, and I didn't discuss this in this talk because I don't have to talk about everything, but in fact, I presented to you models that are adequate if we have a risk-neutral decision maker. And of course, we can ask, what about if we have other types of attitudes towards risk? So it would be interesting to develop stochastic models for risk-averse decision makers. This is totally to be done. As far as I know, there's nothing in the literature. Of course, in terms of robust optimization models, again, I don't know anything in the literature done on that, and possibly there are other things to be done. And this is the good thing in science, is that we always find nice and interesting things to do. Well, since I'm going to share with you the slides in case you want, I leave here the references that I used to prepare this talk. And this is the moment to say thank you for your attention listening to this talk. So I think I'm running out of time, but still I was challenged to talk a little bit about running a journal and computers and operations research in particular. So I will just talk briefly about that, okay? Just 5 minutes about running the journal. I think you are now watching a different set of slides, right? It's about, I think you are watching a new presentation, right?
Yes,
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 yes.
you
Okay.
are right.
This
Yeah.
is about computers and operations research. Actually, as Benji said in the nice introduction, I am currently, and possibly also by chance, I don't know how these things happen, I am the editor-in-chief of Computers and Operations Research. This is what we call a scholarly journal. I like very much usually I like to talk about the journal, of course, and about nice things related with publishing. I'm not going to bother it too much. But one thing that I always like to present is this slide, because to point out that researchers publish the outcomes of science for a long time ago, since a long time ago. If we try to look for the first scientific journal, we can go back to the 17th century, to a journal called Philosophical Transactions. It's interesting that this journal was renamed in 1776 to Philosophical Transactions of the Royal Society, and this journal still exists, which is very interesting. This is actually the first true scholarly journal, which means a journal exclusively devoted to science. Well, in 350 years of scientific, technical, and medical publishing, many things happened. The number of scientists, and these are figures that I tried to grasp for this presentation, actually. I was trying to get as much up to date as possible. There is an estimate of more than 8 million researchers around the world. The number of journals is estimated around 30,000. There is a very increased number in terms of peer-reviewed articles published every year, more than 3.3 million. And we see, of course, a big progression from print to online and many other things. But still interesting. The article has not changed much in these 3.5 centuries. It's still print-based, and it's still on a linear reading basis. Okay, of course there are some changes. For instance, now we have tools for internal navigation, for reference linking, for supplementary data files that you can find online available. We often have the articles available in HTML version, and so on and so forth. Well, science is usually published around publishers. So there are several publishers around the world whose goal is actually to promote science and to promote science to be published. And Elsevier is actually a big publishing company, and Computers and OR belongs to Elsevier. Just to give you an idea about Elsevier, it publishes more than 600,000 manuscripts just in 2021. This amounts to 18% of the total number of scholarly articles published worldwide. Elsevier has currently approximately 28% of citation share, and it has approximately 2,700 active and digitalized journals. Elsevier is organized into broad subjects: health, life sciences, physical sciences and engineering, and social sciences and humanities. It is in this last one that computers and OR is included, but actually this subject is still subdivided into others, namely arts and humanities, business management and accounting, decision sciences, and others. Computers and OR is actually in the decision sciences family of Elsevier. In fact, there are different subfamilies inside decision sciences. Just to give you an idea, here we have all the journals that are in the same family in Elsevier as Computers and OR. I like to see these as a family of journals. And you see here some journals that you know well, like GEJOR or Omega, or Journal of Operations Management, Journal of Production Economics. We are all in the same family of journals inside Elsevier. When we talk about Computers and OR, let me tell you that it is published since 1974. It has now 142 volumes. We publish 12 volumes per year. We have now over 6,300 papers available online. The contents are hosted on Science Direct, and we have over 500,000 full text downloads per year. This is quite impressive, I would say. There's a big team running the journal. I am actually the editor-in-chief, but then we also have an editor for surveys, just for surveys, and then we have 6 other area editors. We have now one in China, and I'm very glad about that, Shuming Guan from Beijing. And then helping the editors, we have the advisory board of the journal that nowadays has 61 members from 22 countries. Well, Computers and Operations Research is a journal that covers different scientific fields, namely fields in which operations research and computers interact. There are many cases: transportation, economics, investment strategy, logistics, I don't know, urban planning, ecology, and so on. So computers and operations research actually provides an international forum for the application of computers and operations research techniques to problems in these or related fields. Okay, so usually there's something in terms of optimization methodology that is needed to solve a problem. And of course, we need to develop some sophisticated techniques in a computer to solve the problems successfully. This is, I would say, in broad lines, the aims and scope of the journal. Computers and OR, over its life, has incorporated several journals, namely 2. One is called Location Science, that was incorporated in 2001, I think. And another is Surveys in Operations Research and Management Science. It has been incorporated more recently, I think 2017 or so. So the journal also publishes state-of-the-art surveys in a special surveys section. Surveys nowadays are very important, in my opinion, because they help either educators, researchers, or students to obtain an overview of subjects of current interest and important recent developments in established areas. For instance, sometimes we are experts in a topic and we want to do something related with another topic. If we have the chance to get a survey on that topic, we very easily get to know what people have done there. Just to give you an idea about authorship in computers and operations research, it's good because we see China dominating. Okay, I think here we have Hong Kong and Macau are possibly separated here from mainland China. I don't know, but you get an idea of the origin of the authors who publish in computers and operations research. So I would say that it's a worldwide journal, clearly. Nowadays, people tend to reduce journals to numbers, to figures. I don't like that, to be honest, because I think the reputation of a journal is more than just an impact factor. But in computers and OR, we cannot complain because we currently have an impact factor of 4, which is not bad. And we don't ask the authors to cite our journal. Never. This is something that is not done in computers and OR, although it is done in many journals. But I never ask that, and I don't allow my editors to ask the authors to cite the journal in their papers. So you can publish in computers and OR without citing computers and OR. And we are currently indexed in different categories, namely computer science, interdisciplinary application, industrial engineering, operations research, and management science. There are other measures for you to see. For instance, an extension of the impact factor is what we call the site score, which is like instead of accounting for 2 years, we account for 3 years. And you see, if you change this, you change the formula, you get different figures. This is what I don't like about these figures, okay? But anyway, for those of you who like to see impact factors and site scores, I would say that we are not doing bad at all. More interesting is to see the size of the journal. You have in yellow bars here the number of submissions a year. So it's more or less stable, around 1,300 a year, I would say. The number of papers published is also rather stable. I would say between 250 and 300 a year. Of course, the green bars do not correspond directly to the yellow bars because some papers submitted in 2021 will appear in the green bar in 2022. because they are published only in 2022. So, but the idea of this figure is just to give you an idea in terms of the numbers involved in the journal. So I would say that we published between 250 and 300 papers a year, and we get around 1,300 submissions a year. So of course, I look very much forward to getting your submissions in computers and operations research. And I thank you really, really much for giving to me the chance of making these two presentations. I'm sorry I took too much time. I always talk too much. I'm really sorry for that. But well,
that's fine, Professor Francisco. Thanks for your very nice preparation and very nice presentation. I think it's a very comprehensive talk with very nice, very novel technical parts and also managerial insights in application. So now let's move to the Q&A section. So for the audience, please kindly type your questions in the Q&A section. And we already have two questions. So first is the question from the Patrick. He is also from HKU. Many thanks to Professor for a very detailed talk. I have a question regarding the stochastic programming approach adopted to your districting problems. Scenarios are considered in your formulation. How would you compare your approach with other stochastic optimization approach, such as L-shaped method and a robust optimization approach? Please, Professor.
Okay, that's a good question. Can I, do you hear me? So I can keep talking, right? Okay, okay, perfect. This is a very interesting question. Well, first, in terms of robust optimization, as far as I know, there's nothing done on districting involving a robust optimization. I think this is a nice research avenue. And to the best of my knowledge, so far no one treated it. So I have no direct answer to this. Usually, I would say that we resort to robust optimization in two situations. One is when we cannot quantify probabilistically our uncertainty. And another one is when it is irrelevant to quantify our uncertainty probabilistically. For instance, if you build a bridge, you must build a bridge to support whatever weight you put upon it. Okay, so you don't use stochastic programming for planning when you are playing for bridge building. Okay, so I would say that I don't like to compare directly stochastic programming and robust optimization, saying this one is better than the other. I think that both are important tools because they capture uncertainty in different ways. So I would say that depending on the specific problem we have, it may make more sense to quantify uncertainty probabilistically, or it may make more sense to go in the direction of robust optimization. Although, as I repeat, I know no work on that. As far as the other techniques in terms of stochastic programming, in fact, I presented here a model that we could solve using a solver. But of course, in practice, if the number of scenarios grows, this is not possible, and we need to resort to other techniques. In fact, in our case, we cannot use directly the L-shaped method because the L-shaped method is like a Bender's decomposition with feasibility constraints. So it's for linear programming, or at least for a second stage linear program, but we can use here what we call the integer version of the L-shaped method. To the best of my knowledge, no one has ever done that for districting. I must say that in terms of districting under uncertainty, the number of papers in the literature is probably 3, 4, 5, not more than that. So I'm talking about an area that is just starting. So I would say that certainly solving this specific problem with more scenarios and applying other techniques like the integer L-shaped method or sample average approximation could be nice possibilities for handling this problem if we have many more scenarios. And this goes back to one thing that I told you during my talk. If suppose that you have an infinite number of scenarios or a very large number of scenarios, what can we do? Well, in that case, the only possibility is that we adopt some kind of sampling technique. When we have many scenarios, the best we can do is to capture a sample of a small number of scenarios and solve it efficiently. And then we can use a sample average approximation framework in which we repeat these several times, okay? I think I answer to all the aspects. So thank you very much, Patrick, for your question.
Thank you very much, Professor. So let's move on to the second questions. This is from Zhang Wennan, who is also from our department. So thank you, Professor Francisco, for your very insightful talk. I want to ask several questions about this topic. First of all, when we consider the reassignment problem, I noticed you use the maximum reassignment in the constraints. So how do we measure the value of the maximum reassignment in real life? So this is the first questions. For the second questions, in some scheduling and resource allocation problems, I'm curious, what do you think about our pursuit of faster computing time? Will this be useful in real life? Peace.
These are very good questions. Thank you very much. Very nice questions. Well, in terms of the maximum reassignment in real life, usually it depends. For instance, suppose that you need time to move people. I mean, if you build the districts, because suppose that we have teams working in each district, okay? So by reassigning a territorial unit from one district to the other, this may mean that you need to reassign some workforce from one district to another. So usually this maximum reassignment may have to do, for instance, if we have one human resource who can visit 4 or 5 territorial units, and you only have the possibility of moving one human resource from one district to another, then possibly you can only reassign 4 territorial units from one district to another. So the answer to this question will be very much problem dependent. It depends on the very specific problem you are working. So you may be constrained by human resources that you have to move, or by a budget for paying for the reassignments. Okay, this also limits the number of reassignments. So it depends very much on the specific problem you are working with, I would say. Okay, so there's not a closed answer to this question, I would say. Okay, as for the second question, this is very curious. I am a guy from optimization. I like optimization very much. My background is on mathematics, although I have worked in statistics and operations research for many years. And I'm a guy from optimization. So I started my life optimizing and being fast optimizing. The issue is that when we come into real life, and you talk about scheduling and resource allocation problems, but we could talk about many other problems. I mean, how relevant is it to really get the optimal solution in as fast time as possible? Well, here, in my opinion, usually our models are just approximate models. And I learned this a lot when I worked, and I have worked a lot in logistics and supply chain network design. And I realized that in real applications, sometimes the data is not very precise. There are errors in the data. So when you build a model, actually, even if the model is totally correct, which is never the case, because no model represents precisely a problem, but suppose that it represented. Even in that case, the errors in the data make the model not the exact model for that problem. So I would say that there are 2 types of issues when we build a model. First, it's the model itself, and then it's the data that we are going to lose the model. So in my opinion, when I see these papers with very sophisticated problems for solving real models for solving real problems, and then people look to get an optimal solution in a very fast time, I would say that, in my opinion, this is not really meaningful in practice, because for people making decisions in practice, for managers, they want reasonable solutions in a reasonable time. And sometimes it's not an issue to wait a few hours for a solution. In the case of scheduling, it depends very much on the application. If you are talking about project scheduling, it may not be an issue to wait 1 day for a solution. Of course, if you are talking about shop scheduling in a factory and you want to adapt your schedule, then it may be important to get a solution fast, even if it is not the best one. Okay, so I'm always for getting insightful solutions. I mean, what I think is important in real life is to get solutions that make or that better support the decision-making process, and not looking for this optimum in very fast time. Although I also do that, but sometimes more for fun than for applying in practice, okay? I'm not sure if I answered in full to the question, but this is my vision.
Yes, thanks very much, Professor Francisco. And also we have just another question appears. So hi, this is Merit Endogan from King's College London. I want to ask that how districting problems are different from clustering, and can't we use a clustering algorithm such as k-means clustering instead of a mathematical model? Please, Professor.
This is the question. This is a very good question. Well, the difference actually, and the reason why we cannot use a clustering, because a clustering method, what we want is to divide a set of elements into groups. And these elements may be totally abstract. I mean, it may be, for instance, customers in a bank that we want to cluster in different categories, for instance. The issue about districting is that there is something that these clustering methods do not solve, which is the geographical context of these problems. I mean, contiguity and compactness are two very important aspects, and they have a geographical representation. I mean, usually they are associated with real distances, road distances, for instance, or travel times. And so when we use an algorithm such as a k-means, we can totally overlook that. This is the only reason why we cannot treat districting problems as clustering problems. But I would say that a districting problem is, let's say it like this, it's a special type of problem. Is dividing a set of elements into groups. The issue is that in this division, we need to take into account for a few features. And moreover, I didn't discuss contiguity explicitly, but in some applications, we actually we cannot use a surrogate measure for contiguity. We need to explicitly have contiguity constraints in the model. And again, this totally destroys the possibility of using an algorithms like the k-means algorithm for clustering, okay? But that's a good question, because in fact, this is a type of special clustering problem, let's say.
Yes, thanks, Professor.